cell, and I have a system, a machine that has a slurry that it puts on a current collector, and then it goes through a bunch of rollers and then it folds up. Right? I can get creases that fold in those folds. Right? That's a clear non-uniformity or a defect. My material might have various different particle sizes. Maybe my particle size doesn't control them. Maybe my separator, the part of the battery that keeps the electrodes apart, has non-uniformities in regions that are more conductive than other regions. Ionic conductive. I can get electrode thickness variations, porosity variations, mechanical deformation. All of these things could go on when you make a cell. But then also, things can happen when you're operating a cell. And I'm not talking about catastrophic things. I'm talking about just natural occurrence during normal cycling. For instance, lithium plating, the generation of gas, or the breakdown of an SEI, losing electrolyte or breaking apart electrodes, various kinds of non-uniformities in mechanics and in temperature. So for instance, this is a tomography, an X-ray tomography picture of a cell, and you can see regions where there's delamination that's occurred due to the processes going on in the system. And so the question that I want to address is, how do these localized phenomena lead to performance degradation? And what are the critical size scales? Right? So what do we need to look for if I'm going to manufacture a battery? And what do we need to look for if I'm going to be operating a battery in order to mitigate such issues? Okay? And so let's talk about that. And the way I want to start this story is I want to talk about mechanics. I want to talk about how stress and strain affect materials in a battery. Okay? And so let's think about the stress in a battery. All right? As we cycle this battery, what's going to happen is it's going to expand and contract. Okay? And so in general, this expansion and contraction is occurring in some kind of constrained environment. It's a can, it's a package, it's a box, something like that, right? And so what's going to happen is that it's going to try to expand, and there's going to be a stress. But what's going to respond to that stress is going to be whatever the softest or the most component that you have in the system, right? And so when you think about the materials that make up the system, you have metals, you have ceramics, but you also have these polymers, separators, binders, things like that. And so when you think about what's going to respond to the stress, it's going to be those kinds of materials. Now, historically, when you think about separators, which is a polymer that separates those electrodes, people usually think about the tensile properties, because those are the properties that matter for manufacturing. But it turns out that whether it's an internal stress or an external stress, separators are primarily being compressed. And so the question becomes, what happens when you compress a separator, right? Well, before we can answer that, we have to think, how big is the stress we're talking about, right? And so the answer is that it depends, okay? But roughly speaking, we're talking about a megapascal of stress in a normal battery that's not constrained. It's a normal pouch cell, okay? And so 1 megapascal, to give you a perspective, it's about the amount of force or stress that you can apply by squeezing your thumb on top of your fist. It's kind of like that. That's about 1 megapascal. So it's not a huge amount of stress, but it's still significant nonetheless. And so if we take a look at stress-strain curve for a typical battery separator material, what you see is a few key regions, right? You have an initial region where you have a very large deformation and very low stresses. And so you're simply buckling pores and you're getting rid of free volume in the structure. But then in the second region, you start getting elastic compression, which then yields to a plastic flow regime before you get to densification, okay? And so that's a typical stress-strain curve. But if I think about the numbers that I gave you, I said that most batteries are around 1 megapascal. And if I look at this, I see that this scale goes up to 60 megapascals. So 1 is really tiny. It's really down in this region here, right? So we're not in a highly plastic regime. We're in a very elastic regime. Now, normally mathematicians kind of look at, elastic regimes as not so interesting, right? I push on it, I let it go, it comes back. But just because it's elastic doesn't mean that nothing happens, right? In fact, something very important happens in the elastic regime. And if we think about a separator, and we think about something that's porous, right? What we can start thinking about is what happens to those pores as I squeeze this cell. And to realize the answer, you just have to think to your kitchen. If you have a sponge in your kitchen that you use to wash the dishes or something like that, and you squeeze the sponge, all the water shoots out, right? Because you're making the pores smaller, you're closing them off. And so a separator is going to work the same way. As you put compression on the separator, the pores are going to get smaller and smaller. And so we can ask the question. We can ask the question of how does the transport behavior work as I start moving through this porous structure? And so we can make a simplified model. Let's think of a Swiss cheese model where I have some holes, some discs that have a certain amount of area, right? And I can define the amount of area with phi, amount of porosity. And I can ask, okay, well, what does the resistance do? The simple, rho L over A type stuff. And then I can modify. I say, well, let me apply a little bit of strain. Let me squeeze it a little bit. And I'm going to assume that the volume of polymer doesn't change. So I'm going to keep the volume fixed. And so if I work through some of the math, and it's not very hard, it's pretty straightforward algebra, what you'll find is that there's a change in resistance that depends on the amount of strain you apply, the porosity that you have, and this exponent alpha, this Lubmin exponent, which is kind of a standard characteristic of a porous material. And so I can kind of say, well, let's see what this does in a real battery. So let's do an experiment. Okay, what I'll do is I'll take a battery separator, I'll make a few layers of it so it's thick enough for my machine to be accurate, and I'm going to squeeze it. And I'm going to measure the impedance across this cell. And so if I do that, I have my equation here that tells me about how the resistance changes. I have my experiment, which is my polymer that I'm going to squeeze down by some amount of deformation. And what I can do is I can plot the strain versus the resistance, or the amount of increase in my resistance. Okay, a fairly straightforward kind of measurement. And what you see here is you see a line that kind of goes up and up and up, and you kind of see there's a red part and there's a dashed part of this line. Well, the red part is the actual data, and the dashed part is the actual model. And so what you can see here is that this very simple resistance model actually works quite well for the resistance change as you apply compression to the separator. And this is purely elastic deformation, right? In fact, we can do this on other battery materials, and the same general behavior applies. In this case, I'm plotting tortuosity versus porosity, which is another metric that we use in these cases. And I can use this to figure out what this exponent is and how well this behavior maps onto the real system. And so it turns out that when you do all of this kind of stuff, what we can say is that compression on a separator leads to pore closure, which leads to reduced transport. The resistance goes up. Okay? Now, we can ask, well, what about this elastic part? Isn't it just going to open up again when I let go of the stress? And the answer is correct. It will do that. But there are things that permanently change a battery. Right? So for instance, if I have a permanent change in the volume of an electrode by plating lithium on it or growing an SEI, that's going to lead to a permanent strain on my separator. I can get creep. I can get viscoelastic creep in the polymer material. And so these are kinds of things that can lead to permanent changes. But the fact is, what I hope to show you later on, I want you to keep this in mind, is that even within the elastic region, this type of deformation can lead to non-uniformities where I have different amount of strain in different parts of the system. So let's keep that in mind. We're going to table that discussion for a couple minutes, and I'll just remind you that electrochemically passive components can be the most mechanically active components in a system. Well, let's see how this plays out when I start having non-uniform flows. So we did an experiment that took us about 2 years to run. It was a very patient graduate student who did this. And what we were trying to do is we were trying to apply a uniform stress to a battery and look at the results. How does the lifetime change? Things like that. So what we did was we took a cell, we put it into a fixture where we compressed it to some level of stress, and we just held it there. We did a fixed strain kind of thing. And then we electrochemically cycled it. Okay, and we did this for about 1,500 to 2,000 cycles, and we did it at a C/2 rate. So to put it in perspective, that's 1 or 2 cycles a day, 2,000 cycles. You can see that it's a long time, right? A little more than Okay, so here's the results. So what we found when we did this study is we found that if I have a high amount of stress, where high is 2 MPAs, remember 1 MPA is about what a atom does, right? What I find is that the cell the capacity dropped off pretty quickly. Okay? If I had a little bit where I was at 0.2 MPA, I found that the cell had a good lifetime. And if I had an even lower amount of stress, it had an even better lifetime. Okay, so that was our result. And this took, again, it took a very long time to generate this data, but it generated useful data because we said, gee, that makes sense, right? If I have a lot of stress, if I squeeze the cell a lot, I'd expect that it would die quicker. And that's when we started, but then we realized, wait, that doesn't make any sense at all. Because aren't batteries electrochemical? Why should the amount that I squeeze on it matter? And so we asked the question. We said, what could possibly lead to this capacity fade? Why is the capacity falling down when we go to higher and higher mechanical stresses? And so we listed a few mechanisms, right? We talked about the elastic deformation that I told you earlier about, that I squeeze, I get pore closure, that leads to reduced transport. And we talked about viscoelastic creep, so I press on the separator over time, it eventually permanently deforms. There could be electrode degradation. So something happens to the electrode and we reduce lithium availability. And there could be SEI or interface growth, lithium plating, those kinds of things. All of those could lead to capacity fade. So what we did was we said, let's see if we can figure out in this system what actually led to the capacity fade. So the first thing we did is we took our batteries out of our constraint and we measured their capacity. And what we found is that as soon as we removed from the constraint, just 10 minutes later, the capacity jumped up. And when we moved it after 10 hours, it jumped up even more. Okay, so clearly, this tells me that this elastic was leading to some of the behavior that we were seeing. Right? Okay, so that's data point number 1. Data point number 2, let's look at the separator. So we go stick it in the SEM. This is what a pristine separator looks like. And as I look at the different stress states, I see that really these pores are definitely closed, right? I mean, we can all agree that that's pretty closed up. You know, this is closed a little bit, this one's closed a little less. I can still see some open pores over here. But generally, I think we can agree that it looks like there's some permanent deformation. So viscoelastic pore closure is clearly a mechanism here. Even in the unconstrained sample, we can see that. Let's take a look at our electrode surfaces. And sure enough, if I look at my pristine anode and I look at the different stress states, I can see that this looks different than this. I can see there's some growth of some kind of crud. There's a change in the surface structure, right? So clearly something's going on there. But it's really hard to come up with an answer when everything clearly shows every effect, right? So we did another experiment. We said, well, this is kind of funny because it seems like there's got to be some main reason. So what we did was we took our batteries apart. And we took each component of the battery and we tested it separately. Okay? So for instance, take a separator out, put that into a fresh cell that has a new anode, a new cathode, cycle that. Put in my anode that I harvest from a cell with a new cathode and a new separator, and I measure that, right? And so I do all of those things. And what I found is that every individual component, the anode, cathode, separator, all of them were fine. None of them showed a significant degradation in performance. They all worked out just great. And so we were confused for a long time. We were basically convinced that all these years of effort were useless because mechanics don't matter. And that, clearly we don't understand anything about batteries. But we did look a little closer. We didn't give up, right? And so what we did is we said, let's look at the battery itself. And so if you take apart a battery, okay, in these particular cells, what we saw was that there was this crud plating on the surface. We lost lithium. Lithium was plating out on the surface here, right? But we noticed that the patterns looked, well, suspiciously similar. Right? And if I were to fold this cell back up again, what we would find is that there was plating in this region and this region. So we can ask ourselves, why would this part of the battery care about what this part of the battery is doing? Electrochemically, they're not anywhere close to each other. The only thing that links them is mechanics. Okay? Stress would say that this whole region is under stress, or this whole region is under stress. So immediately we notice that there is some phenomena that's occurring, and we notice that it's localized. It is a mechanical effect that is localized to one or two regions in my cell. And that made no sense because I believed my students' SEM, right? So I said, how can it be that, well, the student said, well, actually there were more pictures I didn't show you. Oh, let's see the rest of the pictures. And so one of the lessons for students who are doing SEM, other visual characterization, is that it's not good enough to just show me one picture. You gotta look at the whole thing. And what you notice is that all of a sudden those pictures I showed you, right? I showed you separators where that had the pores all closed. Well, actually, that was in a region here. If I looked at that region, it was perfectly good. Okay, and places where I showed you the anode had some crud on the surface were the regions in here, not the regions over there. Okay, and so all of a sudden what we find is that localization is where the degradation is occurring. It's not occurring uniformly. Okay, the deposition of lithium is only happening in some places. Right, and in fact, if we look at it as a function of the stress, we see that, okay, when there's a low stress state versus medium versus high, we can see the amount of plating increases drastically. Okay? So what happened here wasn't really about changes in the material, it was about plating of lithium, and we see that that plating is not uniform. Okay? And so, why does it form where it does? And why does that lead to the degradation that we see? So let's do another experiment, okay? And in this experiment, what we're going to do is we're going to take that battery, and we're going to put, instead of just squeezing it uniformly, I'm going to put a hex nut right on top of it, okay? Like a quarter-inch hex. And I'm going to squeeze that in my fixture. And then what I'm going to do is cycle the battery and take the battery apart. And this was, again, we weren't sure what we were going to get, and so we took it apart, and we looked at the cell, and sure enough, what we get is we get that same hex pattern in the electrode. Okay? And in this case, looking at the anode, you can see that I have regions that show no lithium, you know, under the dark part there show no lithium. I can see this white kind of metallic looking thing, which is lithium plating, and then I have this orangey or reddish color, which tells me that there's lithium interpolation. But you can see that it's not uniform. And more importantly, you can see that it's correlated to the location of the mechanical stressor. Okay. So that gets us close to understanding what's going on, right? We can intentionally squeeze batteries, but if we're going to argue that what squeezes is the separator, let's just cut out the middleman and go straight to the separator, okay? So if I take the separator, I squeeze it with a ring. This is a pattern just behind the separator. You can see that it becomes transparent where you squeeze it, and that's normal for a porous polymer that gets compressed down and get through the pores. I put that into a cell, I cycle the cell, and sure enough, you can see there's no plating in the region where the pores were closed, and I have plating in the regions right next to where the pores were closed. Okay? So that says we're getting closer to understanding what's going on. Okay, there's something going on with this pore closure. There's something that's happening when I squeeze this cell that creates some kind of reason for lithium to want to plate, not under the stress, but right next to where I apply the stress. So we can set up a model. Okay, in our model, we can take sort of a simple model where we're going to take our electrodes, we're going to close off the pores in the center, okay, and we're going to allow lithium to move around through it. And so what we're going to do, get through all this, okay? What we're going to do is we're going to look at all of this transport. We're going to look at how the lithium moves around this blockage, okay? And it's going to move around such that it gets around it somehow. The lithium that's here wants to move this way. Okay? And so how do we get at that? Well, we can set up a standard kind of finite element modeling using typical Newman type models of the kinetics. Okay? Nothing too special here. We're going to use COMSOL to do it. We'll set up our pore closed region that has no transport here, and we're going to allow transport to occur everywhere else. And so this is what you find when you set this up, right? These arrows correspond to the flux of lithium ions. And so what you can see here is that as this moves lithium from one side to the other, we see that it's not uniformly removing lithium. The lithium that's back in here is kind of trapped because it has to move all the way across in order to get to the other side, right? And this lithium that winds up on this side has a driving force for diffusion to move it that way. Okay? But the rate at which it moves across this layer is much higher than the rate at which it moves left or right. And that difference in transport is going to be critical. Okay, so let's freeze that simulation for a second. And let's just look at the concentration of lithium at different places. And what you see here is that as I charge the battery, so I move from the cathode into the anode of the lithium, what you see is that all of this region here has a high concentration of lithium because it all came in and it's kind of waiting to diffuse out. Okay, it takes time to diffuse out. And so even though globally the voltage is uniform, locally, because of this transport variation, I have a concentration gradient within the cell. Okay? Now, big deal, you have a concentration gradient. See, lithium is kind of funny in a way. It wants to intercalate inside of graphite. Okay? But that's only if the potential is in a certain region. If the potential moves out of this comfortable region, it prefers to sit on the surface. Okay? That region happens to be at a local potential of 0. Okay, so if the lithium is potential is above 0, it wants to go into the graphite. If it's below 0, it wants to sit on the surface. So if we map out what the local potential is, what we see is that the potential is not uniform. In fact, this potential has a minimum. And that minimum occurs right next to my defect. And if we look carefully at this plot, what we see is that under the right conditions, or after a certain amount of time of diffusion occurring, it drops below 0, which means the lithium is going to start plating on the surface rather than intercalating into the electrode material. And in fact, if we look at this at different charging rates, so as we move lithium faster, this effect is even more pronounced. And you can see that as I move lithium faster, this peak drops lower and lower, and I can get some very deep peaks which are very favorable to lithium-ion plating, or lithium plating on the surface. Okay? And this is consistent with experiments. We know if we cycle faster, we get more plating. Okay? Okay, but what does that have to do with failure, and what does that have to do with mechanics? And the answer is actually quite interesting, I think. Okay? So let's start with this idea that we have some pore closure. How did that happen? Well, let's postulate that it happened because of mechanical stress. Okay, I gotta start somewhere, so we'll start with mechanical stress. I was charging and discharging, my battery expanded a little bit more in this region versus that region, and those pores got a little bit closed up. Well, what's gonna happen then as I charge my battery is that there's a region in front of that pore closure that's really big for plating. So I'm going to put a little bit of lithium there. But now, that lithium has changed the local size of my electrode, which means this separator is now under a higher level of stress locally, which means that part is going to be compressed, which means I should get more plating in front of it. And so what you have here is a positive feedback loop. Mechanical stress that's local leads to plating. Plating leads to increased mechanical stress, and increased mechanical stress leads to more plating. And so if we actually look at the experiments and we look at our simulations, we see exactly this. So in the simulations, we see a nice compact ring, but if we take a look at the experiments, you can see that I have no plating in the center. This was just a disk. And you can see that the plating starts on the edge and starts radiating outward. And in fact, if I look at this in a three-dimensional mapping, a three-dimensional plot, you can see here that I have a very sharp line where the edge of my defect is, and you can see how the plating extends outward away from my defect. Okay? So even though this is a local phenomenon, we have to realize that the global battery will see this as a loss of lithium. We'll see this as a reduction in capacity. And worse, this kind of stuff is the precursor to dendrite formation, which ultimately could lead to catastrophic failure. Okay? So in fact, global experiments can pick this up. So, okay, so what I hope that I showed you there is that mechanics and electrochemistry are linked, okay? And localized phenomena, such as some region just gets a little bit pinched relative to another region, can actually create positive feedback loops that can further degrade performance in the cells. This is a real problem, right? Well, hopefully not. Hopefully we can do something about it. And so let's talk about how we can do something about it. And the first thing we need to think about, okay, is really how can we quantify this effect? So let's start talking about quantification, okay? So what we can do is we can do another experiment. Instead of just squeezing a membrane, we're going to make particular shapes. You can see a triangle is one of our shapes, and an M. My graduate student who did this work was me with an M. But an M is actually a convenient shape for some other reasons that I'll show you. And what I'm going to do is I'm going to take this piece of separator that I've cut into that shape, and I'm going to put it inside my cell. So I'm going to create a defect that has whatever given size I want and given geometric distribution. Okay, I'm going to assemble a cell, and I'm going to cycle this cell, and I'm going to look and see what I get. Okay? And so I look into the experiment, and you do the experiment the first time, and it works beautifully. Okay, so we're like, this is a great experiment. This is going to be so easy. And then we do the experiment 10 more times, and we see absolutely nothing. Okay, because that's how experiments work, unfortunately. And so how do you deal with that? Well, what we realize is kind of obvious that, well, it's really hard to measure lithium, okay? And we only see the lithium when enough material is played out. But in fact, because there's a lot of statistics in this, what you see, this is 9 different experiments. You can see in some cases I see a nice pattern, in other cases I see a whole lot of nothing. So the way we dealt with this experimentally is we took an average. Okay, so we did a lot of experiments and averaged it all together. So for instance, if I take 16 of these and I average it together, I get a nice looking triangle. Okay, and so that's how we do these experiments on plating. Okay, if you take a look at this triangle defect, right, and I look at the average, this one was produced from 30 different cells, you see what we believe is the, we call it equilibrium structure. Now, what you'll notice in this structure is that there's no plating right at the vertices. Okay, which is a little weird. There's a lot of plating on the edge, but no plating at the vertices. In fact, we did that experiment multiple times. Here's a little animation of how the lithium, this is actually video of data, and you can see here that how the lithium evolves in this system. It starts out just a little bit on the edges, right, and then it gradually fills in along the edge, and then gradually moves outward a little bit. But yet there's still very little at the vertices that we can see. If we do an M, we see another kind of structure that looks quite different. In this case, again, I have plating on the edges, but now there's a whole lot of plating at these vertices, but no plating at those other vertices. Okay, so that's kind of a curious type of thing. Why is this going on? I thought plating was related to the presence of the defects, right? And again, here's a little animation that shows that the plating starts at those vertices and then gradually radiates outward from there. Okay. Let's see that one more time. Okay, so what's going on? Let's start wrapping this up, because otherwise I'm going to lose you, right? And so what's going on is that this all has to do with transport. It all has to do with the relative transport of lithium ions. So if we take a look at the flux of ions relative to cathodes and anodes, and look at the net flux, so the net flux going in when we charge it, what you see is the flux is highest along the edges. It's very low at the vertices, right? And that might be a surprising result to you. You might think, oh, why is it low on the vertices? I would always think that vertices are places where you have a lot of electrochemical concentration. Well, it turns out that that's not really what happens in this system. Okay, this is just another picture of the overpotential. But again, you can see in the overpotential, the potential is highest along the edges, not at the vertices, but along these special vertices, it appears to be much higher. Well, what's going on here is geometry. Okay, and normally we think of a point as being a place where we concentrate electric field. That's correct. But in this case, we're actually talking about ions moving. And so what we need to think about is how many ions can move laterally and how far they have to move laterally before they're able to jump across to the other side of the cell. And so what we did is we said, let's simplify this. Let's not do all these fancy simulations, and can we come up with some kind of, analytic argument to qualify when I think a defect would matter versus when a defect would not matter. And so we came up with what we call the IE ratio, which is the area of the blocked ions relative to the length of their exit. What do I mean by that? Okay, so let's look at our triangles. Okay, and if I look at the triangle here and I look at this vertex, what I can say is that the area under this vertex here is the concentration of blocked ions, right? But it can get out by going left or right or going up. So it has a lot of ways to get out. And so if I say that that sort of wedge takes up about a 12th of the area of the circle, then I can say that the area is 1/12 pi over r squared, the length is just 2r, and I can get a ratio that's 1/6 or something, right? If I do that same calculation along an edge, what I see is that I have now half of my circle that has ions, but I have the same length over which they have to get out. Okay? So what we can see here is that there it's much easier to get, right? Or I'm sorry, it's much harder to get out. So up at the top, these ions have a lot of ways to get out, but these ions here are much more restricted. Okay? If I take a look at the inner vertex of the M, what I see is that a whole lot of ions are blocked, and they have a smaller area to get out. And so as a result, again, the ratio here is higher, right? So what we can see here is that the smaller the ratio, right, the lower the concentration of blocked ions and the greater area they have to diffuse. That means there's going to be less plating because it's easier for them to get away, okay? But if the ratio is very large, then it means they have a lot of places that they need to, or there's not many places for them to get out, and so they kind of get stuck where they are. So that's our simple geometric argument. And we can see that argument play out in virtually all of our patterns, all of our structures. If instead of having a shape like this, we simply have a bar. So here you have a bar that's 1.5 millimeters wide. This one's 400 microns wide. And we can see that here we get plating on the edge, and here we don't. Okay. So again, we can use this IE ratio, and we can determine that for a rectangle, the ratio will always be W over 2, where W is the width. So a smaller width would have a smaller IE ratio. Okay. But let's start getting to a critical size here, right? So it seems to me that when I looked at the triangle, I found that at the vertex it didn't plate, on the side it did plate, which means there has to be some number, some size scale at which plating doesn't occur, because this defect is small enough that the ions can move around, can avoid the defect, and can happily intercalate and deintercalate. And so we can ask, what is that going to depend on? And we know it's going to depend on the transport and the relative properties of the material. And so we can do an experiment and we can make different size defects. And we can ask, when do I see plating? When do I not? And here you can see this is my control, my 1.5 millimeter line, and make sure I get plating there to know that my experiment's working. I go from 50 to 200 to 400. 600 I start seeing plating. 800 I see a lot of plating. 1 millimeter I see a lot of plating. Right? So as the defect size decreases, the plating around the edge is also going to decrease. And so if I plot this out, what I find from these rectangular studies shows me that if I have a defect size that's around 200 to 400 microns, I'm going to start seeing plating. But as long as it's below that, I won't. And that number is consistent with our model. Okay, when we did this in our model, we said, well, if you start getting around 100 to 200 microns, it's below the limit where plating matters. And so what does this mean, right? What does this mean practically? What it tells me is that if you're a battery manufacturer and you care about plating, that you need to look for defects of a certain size, okay? Now, at first, you might think it's really hard to find defects. And it turns out that these defects that you care about are on the order of hundreds of microns. Hundreds of microns are relatively straightforward to characterize. So now we don't have to look for nanometer-sized defects. We don't have to look for micron-sized defects. We only have to look for these larger defects, which will have a substantial impact on the transport in these systems. Okay, so that's kind of comment number one. But comment number two is that we can actually mitigate this a bit. And the answer is within our IE ratio. Okay, so if we want to mitigate this, we want to reduce that ratio. So why don't we increase the places where lithium can diffuse, right? And so we can do some experiments that are more thought experiments than a practical battery material. But suppose I take a laser and I take a band that's say 1.5 millimeters wide, and I cut it into strips. So I create small openings such that I have a bunch of 100 micron wide material, strips, okay? And then I can do my plating experiment, and even though I have the same amount of area that's blocked by my defect, I no longer get plating, okay? Because what I've done is I've given it a chance to get out, okay? And you can see that here in the plots of the potential. If I have a large defect, my potential drops down really low, okay? But if I have a bunch of these lines, my lithium can diffuse around, my potential doesn't drop nearly as much. So if we can break up these defects, we can actually get rid of them. I'm running out of time, so I'm just going to skip the issue on current, but you understand if I increase the current higher, it's going to have more of a chance of plating. But the one that I think is perhaps maybe a little more interesting is if I increase or I change the spacing between these defects, okay? So at some point, your defects are going to be so closely spaced that it looks like a single defect, right? And so if you see here, I have a few different lines spaced differently, and as my spacing gets closer and closer together, it's more likely to get plated. So what that means is that here, where these bars are separated by a long distance, there's plenty of room for lithium to diffuse on. But when they become very close, these two act like they're a single wide bar. Okay, and again, that makes sense just from the transport arguments. Let's say if it's too close together, I'll not get enough transport. And we can see that play out in the potentials. Again, you can see that if they get closer, the potential in the center can drop down very low. One of the other fun ones is we can cut things up with a laser also, right? So here I've cut holes in this with a laser with some kind of crazy patterns here, and you can see again I can get rid of the formation of plating even though I have the same pair. So let's kind of summarize the talk, okay? So what I told you about in this talk really is a story about positive feedback and a story about coupling. Okay, I told you a story about how mechanics can lead to plating in a system, and that you can't really think of batteries as being simply electrochemical or simply mechanical or simply thermal devices. Okay, I showed you an example of how transport non-uniformities caused by stress can lead to plating, but it doesn't have to be stress, right? Anything that gives me this variation in transport from one place to the other in the cell, for instance, temperature, right? Defects in manufacturing, material variations, all of which can lead to the type of localized behavior that's detrimental. But I also showed you some ways to get around it, okay? And so just remember, if you squeeze a battery in closed pores, that can lead to non-uniformities, and that can lead to various kinds of plating. So we want to be a little careful about how we implement batteries. We want to be careful about how we think about defect structure, but it's not the end of the world. We're just something to manage by controlling these sizes. So with that, I want to thank the people who did the work, me, John in particular, Sally, some other folks in the group here, some funding, and thank you for your attention, and I'll take any questions. Smaller and smaller. And actually, I don't have I took it out of this talk, but in our paper, we actually made a sensitivity analysis to different parameters, and you can see how important the various parameters are. So C rate is very important, of course, but so is the porosity in the electrode materials, and these are things that are not always discussed a lot in specifications, because it's that lateral transport that matters a lot. So, you know, again, if you kind of keep the C rate up, your pore size is going to drop down. I don't remember the exact number, but like I said, you can, our paper has that. Good. Other questions? Good.
In the derivation for the change in resistance,
Yes.
you have this alpha parameter, the vector parameter. Do you have any physical limitations?
Yes. So alpha is known as the Brueggemann exponent. I won't flip all the way back to it. You remember, right? So alpha really is the exponent that relates porosity to tortuosity. Okay, and tortuosity is kind of like a measure of how tortuous the path is that something has to diffuse through. Okay, so this alpha is kind of a scale. It's a empirical number, if you will. Now, the interesting thing about it, and I didn't talk about this here, but what's interesting about our technique is actually using our technique to measure alpha. So most people normally assume that alpha is around 1.5 or something like that. It's sort of a generic thing that's used. But it turns out that that's not always the case. Right? So think about a porous structure that's made from stretching a membrane versus one that's made by, say, randomly lining up fibers. We would expect a different kind of pathway that things would have to take, right? So this alpha is supposed to deal with that sort of thing. So, it is, like I said, it's the scaling exponent that relates tortuosity and porosity in a particular porous structure. Okay.
How do you see this research impacting battery design itself?
Yes, good question. So I think that it impacts it in a couple ways. Okay. The first way is, of course, on the quality control side and understanding what I need to look for when I make a battery to be confident that it's a good battery. But more importantly, right, it tells me that we need to think carefully about the separator and about mechanical properties of the different components. So you might say, well, why don't I just go to a separator that's rigid? Let me just go to a ceramic material. But now I have a different design constraint, which is that I have to be able to fold this, I have to be able to process this, right? So we need to find a happy medium. So now we can talk about how do you design, what is the right core structure for a separator or for an electrode material, right? So all of this research kind of fits into that. So for instance, there's a group in Switzerland that's looking at engineering idealized separators that would have very particular type of porosity and tortuosity so that when it does experience compression, it doesn't close up. It still has pathways for transport. Right? So things like this could lead to the development of new materials that mitigate these kinds of fundamental challenges that you find. You know? So things like that are where it gets to. I mean, I don't believe that like taking a laser and making separators is necessarily a commercially practical thing, but it actually is a convenient way to study the physics and chemistry of what's going on, and then that can lead to other things down the road. It's a good question. Fair question. Yeah.
It's a very interesting topic, and thank you for telling me how it works. One question I have is, under those strain, does it increase the thermal stress as well as the mechanical?
So, yeah, so, you know, I conveniently didn't talk about temperature, right? Because temperature is kind of tough to think through when you're talking about these properties, mechanical properties depend on temperature. So one of the things that people contend is that, well, how do you know that it's not mechanics at all? And it's just the heat from squeezing something, and that's leading to these changes, and so really this is a thermal phenomenon, right? And so the answer to that is that we actually tried to characterize the temperature a bit. We did not do as well as a group from Michigan who actually built cells and put thermometers inside and things like that. So you can measure temperature. It turns out that the mechanical effects, they do lead to temperature change. I won't sit here and tell you, right? What I will tell you is that the temperature effect from that is actually quite small relative to the mechanical effect from the defect creation that you have. So it's not so much that the mechanics is causing the anodes and cathodes to shift their potentials in a substantial way. It's more that it is causing mechanical deformations of the separator, which is what we're seeing. And the second answer that I have for you is that when we redo our experiments with pre-stressed materials, so we take it out, so we don't apply mechanical stress, and we just put these closed pores and these other structures in there, and get the same result gives us confidence that our understanding of the mechanics is fair and it's not thermal phenomena. Yes?
Did you do any quantification, like per defect, this is the rate of lithium lost to plating, and then quantify percentage of extended battery life?
Yeah, we did. Actually, my student is working on writing that up now, kind of thing. That's actually a very hard experiment to do. And the reason why it's such a hard experiment is that there's so many mechanisms in a battery that lead to loss of capacity, right? And so in a sense, you know, trying to separate what's loss of capacity due to what we're talking about here versus what's loss of capacity due to, you know, SEI growth and other kinds of things. So we've done things like trying to quantify exactly how much lithium is plated out. That's a hard experiment to do, right? And so ultimately what we wound up doing is really getting a more relational thing, so seeing that, you know, I have a certain amount of plating and I have a certain capacity fade and drawing an empirical plot and getting a fit to that, showing that, you know, with this much capacity fade I should expect so much plating in the system. But it's not, I wouldn't say it's fundamentally based, it's more empirically based from the data that we collect. Yes?
So one emerging avenue of materials is self-healing materials,
Yeah.
or self-recoverable materials. Can you envision a pathway to recover this lithium plating?
So, you know, lithium plating is a challenge for a number of reasons in the battery. So, you know, one of the challenges you have there is, you know, this question, can I get the lithium back into the electrolytic metals? Now, one of the things that happens is that when this lithium plates, a lot of times it gets isolated electrically, because you have these insulating layers, and there's a lot of talk about the mechanisms for sort of cracking the equation. So if it's isolated in that way, it's hard to get it back into the equation, right? But the other thing is that once you start nucleating it, it's also happier plating, so your local potentials change. So I don't know, I can't think of a scenario necessarily where just the simple material itself would progress. But I could certainly think of control areas where you could use. So for instance, if I know, let's just do a thought experiment, okay? Think if I have an electrode where I can magically put current at any location I want, right? If I had a grid and I put current wherever I want, you can envision a case where if you knew that lithium was plating here, that you can now do something to your battery. Now, in our case, one of the big things that we worked on for a number of years was really looking at, can we use these methods as methods to control a sequence map. So imagine a car that has, you know, 100 or 1,000 cells, and if I can measure the mechanical stress on each cell as a function of time, I can determine which cell is getting a little more plating than the next one. And now I can manage my overall system to maybe tax that one a little less and distribute my current accordingly, right? And so I think that's where you have more value in this type of approach, which gives us an understanding so that we can put it into control modules and use that to better manage systems. Good.
Okay, so let's take the discussion to the Valhalla, I guess, and we'll have a reception there. For the undergraduate students still left, I think it's a good opportunity to talk to Professor Arnold. You guys are always hiring, right? Talent graduate students.
Always rose up good grad students.
So please feel free to talk to them. All right, see you.
Good. Thank you all.